Okay, so the next speaker is David Mukamel, and he's speaking about long-range correlations in driven systems.
I would like to thank the organizers for the opportunity to participate in this meeting, which I find really exciting. Okay, I would like to talk about driven systems and long-range correlations in them. And particularly, I'll talk about some work I have done with Satya Majumdar and Tridib Sadhu. Tridib was a postdoc then at Weizmann Institute. And then a different subject with Anupam Kundu, who is also here, and Ori Hirschberg from Weizmann Institute. Okay. Okay, so the problem is the following. I want to, typically it's well known that driven systems or systems out of equilibrium build long-range correlations. And what I want to do in this talk is discuss two examples where such correlations show up and talk about analogy between this type of phenomenon and electrostatics in some systems. So I want to talk about two problems. One is local drive perturbation. That is, you take a system which is diffusing in equilibrium, and then at some point you make a local perturbation which is a drive. It's not coming from a potential, and you ask how does it affect the system in general. So that's one problem. The other problem I'll discuss in the second half of the talk is correlations which are built up in the transport model. We want to talk about the transport model with say, a conductor coupled to heat baths with different temperatures. And I want to consider a model where both energy and momentum are conserved, and to look at how correlations are built up there. So the first problem is that of a local drive, and this was done, as I said, together with Tridib Sadhu and Satya Majumdar in this work. Okay, the problem is the following. If you take a system just diffusing particles, suppose you think of a lattice and particles just diffuse along on this lattice with rate, say, 1 in each direction. This is equilibrium problem, and clearly the density is just homogeneous. Now, suppose you make a perturbation and you change the potential locally at some point, only here. Clearly, you are not going to feel it away from the point where you change the potential, right? Because you have a Boltzmann distribution, and only locally the density could be a little bit lower or higher depending on the potential, but otherwise you are not going to feel it. Now, the question is, what happens when you make a local drive rather than change a potential? That is, suppose you take this lattice, and you have the particles diffusing around, and you change the one bond only, such that the rate of going from this side to that side, instead of 1, becoming 1 minus epsilon. So you make a drive in one direction, and you ask how far is it going to be felt away from that drive. Okay, so that's the problem. And the main result is the following. I want to consider the steady state of the system in the presence of this local drive. Okay, so the main results are for dimensions which are larger or equal to 2, then the density is going to decay away from the to its steady state, is going to decay like a power law with a power which is 1 over r to the d minus 1, where d is a dimension. And the currents satisfy that they are just the derivative of that, which is just 1 over r to the d. That's the main result. Same is true is not only for a single bond which is driven, but if you take any local arrangement of bonds or local arrangement of drive in some area, this is going to be true, except maybe the power laws are going to be modified. We've also calculated the two-point correlation functions, not only the steady-state density profile, but the two-point correlation function. And it turns out that the two-point correlation function is going to decay in 2 dimensions, like this is CRS, the correlation between 2 points R and S. is going to go like roughly 1 over r to the power 2d. This is going to be, the density is going to decay like a dipolar field, while the two-point correlation function is going to decay like a quadrupolar field in 2D dimension, in 4 dimensions. Okay, so we have shown that if the density of the particles is a half, we can show it to leading order in epsilon if the density is not equal to a half. Epsilon is the drive, is the parameter that controls the drive. That's the rate. Right. This is epsilon. Okay. Okay. So let's just very quickly show the result. Here is the density. The density profile along the x-axis. This is the drive, and the particles are diffusing with exclusion. That is, there is at most 1 particle per site, and this is the density as it is measured, and you can show that it goes like 1 over r. This is in the x direction. It goes like 1 over r, except in the y direction. If you go perpendicular to the drive, it goes like 1 over r squared. Okay. Now, how do you see that? It's rather, to analyze the density is rather simple, straightforward. You write down the equation of motion for the density phi of r and t. This is the density at the site r. And it basically, look at non-interacting case first. That is, particles do not see each other. There is no exclusion. Then you have a diffusion equation. Particles are just diffusing. But if you look at the equations on both sides, which are basically the bond, you see that there is a term which goes like that. It just, the equation is just a little bit different by epsilon phi 0 t in the equation. So basically, only these 2 sides, on every other side, it's just a diffusion equation. But on these 2 sides, r equals 0 and r equals r1, that bound driven bond, it's a little bit different. So if you look at the steady state, where this is 0, but what you see is that the equation is just basically electrostatics of a dipolar field. That's what the density is satisfies. And the only different from the usual electrostatics is that here the strength of the dipole has to be solved self-consistently. It's proportional to phi of 0 to the potential at that particular site, and of course it's proportional to the epsilon to the drive there. So basically you have this equation that controls the density, and it's what you see is that you feel the fact that you have a local drive, you feel it very far away because it's just a dipole, and that's a dipolar field. Okay, how do you determine phi of 0, the strength of the dipole? You just look at the Green's function of this equation, and basically the solution is just that phi of r is just rho, the average rho that you started with, plus the Green's function that originates at 0 and 1. So basically that is the solution. You know what is the Green's function of the discrete Laplace equation? It just, that is, you put a charge at the origin and you ask what is the potential at site 1, 0, at site 2, 0. So this is well known, and these are the figures. And at large distances, the Green's function goes to logarithmic, diverges logarithmically. That's just a potential, and basically this is the solution. Now, to determine phi 0, what you see is that you just look at this equation. You know that the g of 0 is just 0, g of 0, 1 is just minus quarter. From knowing the Green's function, you solve this equation for r is equal to 0, you get an equation for phi 0, and basically that's the solution. So phi 0, the strength of the dipole that you have there, is just equal to rho times 1 minus 1 over epsilon over 4. So it's a so that's the story. Then you can also so basically that's the solution. It's a dipole field which is the density, determines the density profile. It goes like 1 over r. And the current, which is just the derivative, it goes like 1 over r squared. Okay, if you have multiple particles, driven particles, the story is the same. Basically, if you look at far away from that region where you have this local drive, it's as if you have a linear combination of many dipoles, and you can determine the strength of them self-consistently by writing down the equations, and you can get the field, the density that you feel far away is that of some configuration of electric charges which is distributed in a local region. For example, if you have two driven bonds in this direction, one on top of one close to the other, you basically get a quadrupolar field, as you can expect. In higher dimension, or indeed different dimension, in dimension 1, you get just a discontinuity of the density near the. It's like a battery. You get a discontinuity, and in dimension larger than 2, you get 1 over r to the d minus 1, as expected. Now, what happens when you introduce exclusion? That is, now I want to take the interacting case, which is the more interesting. Now, in this case, basically, if you write down the equation for phi, you see that the diffusion operator stays the same. The only difference is that the equations, the two equations which of these two sides which bound the driven bond are going to be modified. And the modification is just in the coefficient here. Instead of the coefficient being just phi of 0, the density at 0, it's just a correlation function. It's a correlation function between tau of 0. Tau of 0 is the variable that determines whether there is a particle or not on side 0. And 1 minus tau of 1, 1 is this side, that is, so it's the correlation function of the densities between these two sides. So apart from that, basically the problem becomes the same. So again, you have this dipolar field, which determines the density, except that to control the strength of the dipole, you have to know the correlation function. Okay, so basically that's the structure stays the same, and you can solve this correlation function perturbatively in epsilon, and you can do it order by order. Okay, here just as a result of a simulation result. This is for the non-interacting case. That's the what you see is the way the density decays along the x-axis. And for the interacting case, it's basically the same, except that the slope is the same, except the constant is different. And okay. Now let me go to the more interesting case, which is the correlation function, which is tau of r, tau of s. To take 2 points, and you ask what is the correlation function. In 2 dimensions, it has been discussed by Bodino, Derrida, Lebovich some time ago. The correlation function, in 1 dimension, sorry, it takes this scaling form. That is, the correlation between two sides decrease like 1 over L. L is the strength, the length of the lattice. Here in these 2 and high dimensional systems, the correlation does not really decay with 1 over L. The reason is the following. The reason it decays like 1 over L here is because when L goes to infinity, the current goes to 0, basically, because in 1 dimension, because the gradient, the current goes to 0 because there is no gradient here. And therefore, the effect, the non-equilibrium effect, goes to 0, and the correlation function goes to 0. Here, when we talk about this...
Periodic boundary condition?
Sorry?
Periodic
you can either periodic or just open boundary condition. It's basically, even if it's periodic, when L goes to infinity, when L, you can do it either way. And
but to have a current, you need somewhere for the current to go.
Right. So you can either infinite system, you know. Yeah. Sorry?
You can't just have hard walls.
No, no, not hard walls. You can open system or whatever. Right. Sure. Sure. Now here, in this configuration, the current does not go to zero in the thermodynamic limit. There's always local currents around this area which are non-zero, and therefore the correlation function does not go to zero. If you want to analyze the correlation function, the way a very instructive way to look at it is look at the symmetry. Look at this quantity. First of all, it's clear that there is an inversion symmetry. It has to satisfy inversion symmetry. That is, if you invert both epsilon and, by the way, I'm considering now a symmetric case in which the drive is 1 minus epsilon in this direction and 1 plus epsilon in that direction. It's just more convenient to do it this way. It doesn't really matter. Now, with this configuration, if you reverse the drive, epsilon goes to minus epsilon, and you make an inversion, clearly the correlation function is the same. Also, if you make a particle-hole symmetry, that is, go from density rho to density 1 minus rho, and at the same time we invert epsilon, epsilon goes to minus epsilon, again you get the same correlation function. So therefore, when the density is equal to a half, you have an inversion symmetry. You combine these two, you see that for a given epsilon, C of Rs is C of minus epsilon Rs, or you have an inversion symmetry. Now, if you write down the equation for the correlation function, it turns out that the equation for the correlation function looks like that. It's Laplace operator, it's del squared R plus del squared S of C. That is, it's Laplace operator in 4 dimensions now, because you have to take both R and S into account, equal to something. Something is this charge, which is a very complicated object that I will want to talk about. And so basically, the behavior of this correlation function is like behaves like electrostatic potential in some charge configuration, which one wants to analyze. What is this charge configuration that goes in there? Now, the consequences of symmetry. First of all, the net charge is zero. That is, if you take periodic boundary condition, or then clearly the net charge is zero, because if you just integrate this equation with periodic boundary condition, you get zero here, and therefore the integral over the charge is zero. At rho equals a half, you have inversion symmetry. C of R and S is equal to C of minus R minus S. Thus, a charge cannot support a dipole. That this charge cannot support a dipole because it's a symmetric function. The correlation function is a symmetric function. And therefore, if you do a multiple expansion, then the first multiple that can come into the equation for this charge is a quadrupole. So therefore, generically, you would expect that the correlation function would decay at large distances R and S like a quadrupole in 4 dimensions. It goes basically like 1 over R squared plus R S squared to the power D. That's the behavior, and that you can get right away from the symmetry. Now, what happens if the density is not a half? Then you don't have inversion symmetry. But when you do perturbation theory in the charge, you can show that the charge goes like epsilon squared. Epsilon is the drive parameter. And therefore, this implies that because of the symmetry that when epsilon goes to minus epsilon and you make an inversion, it has to be invariant. It cannot be a dipole again. And therefore, to leading order, to this order epsilon squared, it should also be a quadrupole. And you get this like that, the quadrupolar field. in principle, you can make an expansion. C of Rs is epsilon plus epsilon squared, that plus, you can expand it in epsilon. All odd terms in epsilon should be odd under inversion, and all even terms in epsilon should be even under inversion. Alpha 1 is 0 because one can show that the expansion starts with epsilon squared, and therefore, if there is a dipole, it can come only from epsilon cubed. So to leading order, we can show that there is no dipole, and the leading order is a quadrupolar order. So this is just to show you the distribution of the charge that I talked about. This is the equation. This is you can be written as 3 different types of charges, which are concentrated either along the diagonals or along the axis R1 and R2. One can analyze this. I will not enter into it. It's rather tedious. These are expressions for the charges, but one can show that this is indeed that you can get a quadrupole, or localized quadrupole charge in that configuration. Okay, so if I summarize, I have shown that when you have a local drive, in D larger than 1 dimension, then the density profile decays like that of a dipole in D dimension, that the 2-point correlation function in 2 dimensions decays like a quadrupole in 4 dimensions, at least for rho density equals a half. Other densities, we can show it only to leading order in epsilon, which is epsilon squared. So basically, that's the issue of the local drive. Sorry? Okay. Let me now go to a different example, completely different example, and discuss the correlations which are built in a stochastic model of heat conduction with conserved momentum and energy. This work was done with Anupam Kundu, who is around, and Ori Hirschberg, former student of mine, and this is just posted here. The issue is the following. We want to look at a stochastic model of heat conduction which conserves both momentum and energy. And the model is the following. Take a lattice model. At each lattice point, you have a variable p, which we think about it as a momentum. Now, you want to make a stochastic, and it's coupled to a thermal bath on the right and another thermal bath on the left. Now, the dynamics goes as the following. You pick up 3 sites, 3 nearest neighbor sites at random, and you mix the momenta, keeping the energy and the momentum constant. That is, you take these 3 sites and you change them to q's, from p's to q's, such that the sum of the p's is the sum of the q's, the new momenta, and also you conserve the p squared. Okay, that's why you need to do it with 3 sites if you want to have 3 to conserve both things. Basically, the way it's done is, you see, this is a kind of sphere, and this is a plane. So in this space is the q's form the intersection between a sphere and a plane. So there is a circle, and the q's, you can choose the q's such that you can choose the q's at random, uniformly distributed around the circle, which is the intersection of these 2 objects, the sphere and the. Okay, so that's how it's done. Now, at the boundaries, it's coupled to 2 thermal baths, and the distribution there is just Boltzmann distribution with temperatures T left and T right, and that's it. So you keep on doing that process, and you ask, what is the steady state of the system? How does it look like? What are the correlations that build up, etc. Okay? Well, if you choose this one, say, then you mix these 3. Okay? That's why you have 2 sides at the boundary. You need 2 sides. Yeah, just to, Okay.
You need minimal 3 sites to have this stochasticity, basically.
Right. If you want to conserve both. Okay. This is a generalization in some way of the KMP model, where you have the same thing, except that the variable there is not the momentum but energy. And then you take 2 sites and you just mix the energies. But then you don't keep momentum conserved. Okay. So the question is, how does momentum conservation affect the thing? Okay. The main result is the following. First of all, Fourier law is satisfied. That is, if you look at the energy profile along the limit of large system, you see that it's linear and there is heat conduction, which goes like a gradient of temperature. And okay. Then you can calculate you want to look at somehow the steady state and the deviation from local equilibrium. That is, you want to look at the kurtosis, which is at site I, you look at pi squared minus 3pi squared, which is the deviation from a local equilibrium. In equilibrium, of course, you have Gaussian distribution. This is 0 here because since you have this temperature gradient, this kurtosis is not going to be 0. Also, you are interested in correlation function, for example, energy-energy correlation function, and you want to know how does it look like. Okay, one can show that in fact there is a scaling limit, that the kurtosis behaves like scales like 1 over L times k of I over L, and similarly the correlation function scales like 1 over L. That is, of course, as the system becomes larger and larger, the correlation function and the deviation from local equilibrium are going to decrease. And we can compute both Ki and Cij, and this is a really very intricate calculation carried out by Anupam, who is again here. And Cxy, this is this correlation function. It's equal in this scaling limit. It's equal to some 2 delta t squared. Delta t is the temperature difference between the two ends, times x times 1 minus y if x is less than y, and y times 1 minus x if y is less than x. So you can calculate the correlation function that appears there. Also, the kurtosis itself is just proportional to x times 1 minus x, and with a coefficient which is this. And interestingly, there is a factor of 3. The kurtosis is 3 times the correlation function when x is equal to y. Okay. Now, I just want to outline very briefly the kind of how this goes analysis. What you see here, this is the master equation. This is the rate PL of Pi and T is just the probability distribution of the momenta P's. This is the rate of outgoing. That is, if you start with the state Pi, then it just L plus 2 times P. The reason is each time you pick up a triplet, you just go out of this state, and there are L plus 2 choices of picking up triplets starting from 0, this side, up to that side, and therefore this is the rate at which you go out. The rate at which you come into a state P is you come to this state from a state in which all the P's are the same as the original P, except a triplet of them, a Qi minus 1, Qi, and Qi plus 1. And they will, by making the collision term, they will go into the Pij. And this happens with a kernel K. And this kernel just has to satisfy that the sum of the Q's has to be equal to the sum of the P's. Yeah, Qi is the sum of the Q's, Pi is the sum of the P. And the energy has to be the same. That is, the sum of P squared is the sum of Q squared. Basically, this is the master equation. And there are some boundary terms I will not discuss. Okay? And in this master equation, you look at the steady state, so that both terms have to be equal. And of course, if you have equilibrium, then the solution is clearly just the product of the Boltzmann weights, and it's just like that. The temperature is T. Here, on the other hand, you have local, when the two temperatures are not equal, what you have is a local temperature, Ti, which basically is linear slope. You go from right to left. But there are some corrections to this product state, and these correlations which build out in order 1 over L, and they contribute to the correlation function, to the kurtosis, to the behavior of the system. Okay, Fourier law is satisfied, as I said, because first of all, you can look at the energy current. This is the Fourier law. You look at the current that passes a certain bond here. This current is passed through this bond if you pick up this triplet and you look at the energy that is transferred to that side, or you pick up this triplet and you look at the energy which is transferred across this bond. You write it down. It doesn't really, it's straightforward. And what you see is that the current between I minus 1 and I is just this combination of the energies on these sides. Okay? Then in steady state, of course, the current of Ji minus 1I should be independent of site I, should be equal. You write down the equation, and what you see is you get this equation for I between 1 and L. And of course, the boundary condition is that at the boundaries, the E's are just the temperature, or in the left, it is the temperature at the left, and on the right, the two sides are temperature to the right. So you basically have to solve that. This is a simple equation. You go to the continuum limit, it's just second derivative of epsilon equal to 0. It's linear slope, except that because of these boundary conditions, there are going to be some structures at the near the edges. So this is a very small system just to stress the effect of the edges. This is the linear slope, and what you see, it's a little bit off linear, but as you increase the system, this region where it deviates from linear slope is just localized around the boundary. There's nothing interesting there. Okay, steady state distribution. Let's look at the correlation functions. Okay, we are interested in calculating, say, the kurtosis, pi pj correlation, or pi squared pj squared correlation, etc., or other correlation functions. Here is a result of simulations. This is a kurtosis scaled like 1 over L, and you see that it's the scale 1 over L behaves very nicely. This is the correlation function of the energy correlation function of pi squared times p L over 2 squared. One point is at the middle, and the other one is I, and you see that it goes like something like that. Also, pi pj, the two momenta correlations, basically is 0. It fluctuates. Look at the scale here; it's very small. It is basically 0. So this scaling suggests that, in fact, this is that Pij is indeed 0. The correlation function and the kurtosis would scale like 1 over L. That's what. Yes.
Sort of simple way to understand why there is symmetry around x equal to half. I mean, why these curves are symmetric scaling functions.
They are not really symmetric. There could be deviations from that, but yeah, or something. Yeah. Yeah. Okay. Okay. So let's look at. So these are the results, and let's see how you see them very briefly. I just want to outline. To look at the p squared correlation, to show that pi pj correlation, basically the momenta correlations are 0, you basically take the master equation, multiply it by pi pj, and integrate. And as a result, what you get is these equations, for pi pj. And what you see, this is the pi pj for I minus j larger than 3. And the equations are different if I and j are nearest neighbors or next nearest neighbors. So these are these two equations. These two equations are homogeneous equations in Pij. There is no source term, and therefore p equals 0 is a solution of these equations, and basically that's what comes out. On the other hand, if you look at fourth order correlations now, then there are 5 types of fourth order correlations. There is the kurtosis itself. There is energy-energy correlation. Now you can think of pi cubed pj. You can also think of pi squared pj pk, and pi pj pk pl, 4 different sides. So basically these are 5 types of correlation functions which are fourth order. Now you can write down equations for all of those by just multiplying, the master equation by the appropriate operator and integrate. And this is closed set of equations. So basically, you get here an order L to the 4 coupled linear equations in all these correlation functions, which you in principle should be able to solve. This is a really highly complex thing, and Anupam really has done a great job in looking into that and deciphering the structure of this equation. And what happens is that this, in the end of the story, is that in fact, these types of correlations functions do not contribute in the scaling limit to the equations of these two, ki and cij, and therefore you can concentrate on these variables and write down the equations of them. You can show that this is not going to contribute in the end, and therefore you can analyze it. The structure of the equation is going to be like that. In the steady state, the correlation function, this is for the kurtosis. Ki is a function of ki minus 1, ki plus 1, and it's also coupled to the correlation function. I'll talk about these terms in a minute. Similarly, for the correlation function, you get a similar equation for Cij. This is for I and j far from each other. In the case where they are close to each other, that is nearest neighbor or next nearest neighbor, you get a different set of equations, which I did not write. There is no point. Now, what are these two terms? These two terms are lambda 0 is a function of the energies, which we know, right? This is the profile, the pi squared, which one already solved. The other term is a function of this higher other correlations function, like p squared times p. So it's the other correlations function. That, as I said, in the end, they are not going to contribute to the correlation function ci squared, ci, and okay. So these are the two kind of equations, and you can write down, of course, similar equations for the nearest neighbor type of particles and for the other correlations functions as well. Okay. So one ends up with the following equation for Cij is of the form that delta, which is just Laplacian of Cij, is a function which is there is a source term at when I is equal to j, I plus 1 equal to j, I minus 1 equal to j, I plus 2, and I minus 2. So when it's nearest neighbor or next nearest neighbor, the equations has some source term which looks like that, where this a, b, c, whatever can be calculated and is a function of the correlation functions. So it's a discrete Laplace equation which looks like that. Basically, the charges, looks like charges, they are concentrated on 5 diagonals along the main diagonals, right? It's, if you look at it, it's when I is equal to j, this is the diagonal term, this is 1 off, and this is 2 lines off. So there are charges which are concentrated, sorry, what am I doing? Oh, here. Okay, so charges which are located along these 5 diagonals. So the equation that you have is Laplace, the del squared, ij of c is equal to 0 here and here, except on these 5 lines, which is there is some charge. Okay, you go to the scaling limit, and basically, when you go to the scaling limit, the equation, these 5 lines, the 5 lines collapse into a single line in that limit where L goes to infinity. And basically, you have an equation, which looks like that del squared c is equal to delta of x minus y times some charge, which is the sum of the charge of these 5 lines when you collapse them on each other. And as I said, in this limit, it turns out that these correlation functions, the other correlation functions, do not contribute. Okay, so the problem is reduced to the following problem. It's electrostatic problem on a square where delta square c is equal to 0 everywhere, except on that line. There is a charge on that line. And the potential has to be, this c has to be 0 on the boundary. Okay? So that's the story. You can calculate the charge. It's just a function of the energies, energy profile, which you know. And the steady state equation is basically that, in the end, that del squared c is just this delta function, where the charge is a constant charge along the diagonal, and it's equal to minus 40 delta t squared. And the kurtosis is just 3 times the correlation function. This electrostatic problem can be easily solved, and this is the solution, and that's where you get the correlation function. So C is just, it's a solution of this equation, just x times 1 minus y if x is less than y, or y times y minus x if y is less than x, and this is the kurtosis. This is just to see that how it goes. Some simulation results for the kurtosis, for correlation function, for the various y's, you know. This is as a function of x, the correlation function as a function of x for some different y's. This is y0 half, a quarter, 3/4, and that's how it goes. So with that, I would like to summarize. This is a simple stochastic model of heat conduction. Fourier law is satisfied. One can calculate the correlation function and the kurtosis, the deviation from local equilibrium, and they are 1/L order. And in both examples that I have shown, this the analogous to electrostatic problem is very apparent, and you can see the long-range correlations that arrive from this equation. Thank you.
In the first part of the talk, so you had a drive on a bond, basically.
Right.
Instead of that, so let us say you make it on a loop. That is, let's say you pick a square, and so current is basically moving in loops.
Right.
Then does that mimic a magnetic field, or how does the curl?
You can make analogy to a magnetic field. You can define a magnetic field that which in the end, if there is a magnetic field, there are currents. If there is no magnetic field, there are no currents. That's the analogy. The magnetic field is basically, you can define it if you have a current that goes this way, if you have a current that goes this way, then there is a field that goes up here and down there, and for each bond. And in the configuration you are suggesting something like that.
Yes.
Of course, you are going to have non-zero magnetic field in the end, and
Yes, and you can calculate how the magnetic field
Yeah.
goes away from this thing.
Well, here in this particular case, it's just in this particular case where you have exclusion interaction, it will not go in. It will just be flat.
Oh, okay.
Yeah.
Thanks.
It's just localized here.
Okay, so maybe a question I don't really understand when you say that the local equilibrium is not satisfied at finite L. I think it is a general rule in some interacting particle system.
Yeah, but you want to calculate how is it not?
Okay, but it is a general features of a lot of interacting particle systems at finite L. You don't.
In the in the hydrodynamic limit there is always a 1 over L. Yeah.
Ah, okay. Okay, I thought that you think it was a special feature.
No.
Other questions? No. Okay. Thank you.